Hi, I'm Agah, a postdoctoral researcher from Polytechnique Montreal. This educational course is based on the Oreo and I project, which answers how to run open and reproducible neuroimaging experiments from study inception to publication. You can scan the QR code to see the complete Jupyter book and read the published article if you're interested. And this session will focus on data acquisition aspect, primarily for brain data using MRI. Then we'll take a brief look at other modalities such as PET, EEG, and MEG from the open source acquisition perspective, and we will conclude with reproducible stimulus presentation tools. Let's start with MRI, where innovations often come in the form of a new pulse sequence, in other words, the acquisition software that drives the scanner, or some reconstruction algorithms to reconstruct images from the raw MRI data. Unlike post-processing methods, software at this level is not easily accessible given the proprietary business model of MRI manufacturers. To showcase the main setback caused by this issue, let me present two hypothetical scenarios that demonstrate the difference between using MRI acquisition software and mobile apps on our smartphones. In the first scenario, someone agrees to give you their number on the condition that you only use WhatsApp for messaging. I am sure that you don't expect to hear a response saying, "Oh, I have an iPhone, I cannot use WhatsApp." We don't accept certain apps to be vendor exclusive. WhatsApp is one of them, because we all know that anyone can download it either from Google Play or from the App Store. This is the real reform that made smartphones what they are, to decouple software from the hardware you purchased. And we enjoy this vendor-neutral convenience every single day. In the second scenario, you visit an MRI center and they have a new acquisition software that acquires beautiful fMRI data. The moment you ask, "Can you share the sequence with me?" you know that the first response will be, "Which scanner you have?" If your scanner is manufactured by a different vendor, you won't be able to run that fancy research acquisition. No matter how skilled you are at running MRI experiments, this problem can leave you in the middle of despair, just like Malcolm in the Middle, because MRI research is unfair. The thing is, inaccessibility is not the only adverse outcome. Proprietary acquisitions lock up MRI innovations in their birthplace. Just as an example, let's look at how many quantitative MRI biomarkers are imprisoned in vendor black boxes. With this PubMed search string, we hit 18,000 articles that mention quantitative MRI biomarkers in the last decade. How many of these methods do you think are widely adopted? 8,000, 43, or 3? Unfortunately, the reality is only a handful of methods, and it rarely has to do with what these methods offer. Here is an example. G ratio, the ratio of the inner to outer diameter of a myelinated axon, a biomarker for conduction velocity. But it is not freely available to anyone, because to get it right, you need delicate calibrations, and this is difficult unless we can make the sequences findable, accessible, interoperable, and reusable across imaging sites. When we cannot achieve uniform access to unified implementations of acquisition software, even gold standard methods such as inversion recovery T1 mapping can show site-specific differences on an agreed protocol. You can visit this interactive dashboard to see some examples of such a variance. An effective solution to this problem is open source MRI acquisitions that are vendor neutral, transparent, and easy to deploy. Fortunately, there are tools to achieve this so that we can make MRI fair, findable, accessible, interoperable, and reusable. The first open source MRI acquisition tool is PulseAgg. At its core, you can imagine PulseAgg as bids for MRI pulse sequences because it has a specification component that standardizes a collection of MRI hardware events as an acquisition software. On top of that, PulseAgg provides tools in different programming languages such as MATLAB, Python, or a graphical user interface to write sequences that comply with this specification so that the same sequence can be run on scanners from different vendors. If it sounds too good to be true, you can take a look at publications that use PulseAgg. There are currently more than 50 studies, and in this example, it's a vendor-neutral MP-rate sequence for consistent cortical thickness measurements, which I believe is highly relevant to this audience. So let me tell you how to get PulseAgg to your scanner. First, you develop or download an open source sequence, then export it in a PulseAgg file. This sequence file must be translated to proper hardware commands, which is different for every manufacturer. That's why you need an interpreter that is compatible with your system. To get the interpreter module for Siemens or GE, you can contact the PulseSec team at this link. There are some requirements though. First, you need a research agreement with your vendor and your scanner site. Then you need some know-how and access to install sequences to your scanner. These are the same requirements for running a work in progress sequence you typically obtain through a C2P agreement, but in the case of PulseSec, you go through this procedure once and then enjoy open source PulseSec sequences whenever you want. There are other open source tools that can develop PulseSec compatible sequences such as GammaStar. In addition to PulseSec, GammaStar provides Philips compatibility and it can update the acquisition through the scanner control interface even in real time, if that's what you need. The third option is Venus vendor neutral sequences. It uses SpinBench to create hardware events, then runs them on Siemens or GE scanners through the RTHawk real-time imaging platform. RTHawk is an FDA-approved standalone MRI operating system, so you need to purchase a license to run. But you can still publicly share all the sequence implementations and other people can inspect them because SpinBench is freely available. Okay, good, these solutions exist, but why should we care about open source and unified sequence implementations? When you check either your operator manual or international standards on biomedical measurements, you'll see that MRI scanners are not measurement devices. But for us researchers, MR images are more than pictures, they are data. We all perform some kind of measurement using our scanners. And there is no reason for vendors to care about the accuracy or precision of our measurements when they're implementing their stock sequences. To make one of the simplest yet the most famous structural imaging sequence as an example, which is MP2RAGE, you add an immersion pulse to a 3D spoiled gradient echo sequence and it gives you high resolution T1 weighted images with feasible scan durations. It looks easy on the sequence diagram, but when you look at the implementation details, there are too many degrees of freedom. Not all these parameters are accessible to end user, so when implemented differently, they will lead to differences in image contrast and this will affect your measurements, either for morphometry or for the quantification of physical parameters. I'd like to show an example how vendor neutrality can solve this problem. First, we run one GE and two Siemens scanners using respective vendor native sequences for measuring myelin sensitive parameters. Then we run all three scanners using Venus vendor neutral sequences that can bypass the vendor interface. In the vendor native case, we have completely different user interfaces and we cannot set the exact same protocol despite that we have quite similar hardware on both scanners. Then we acquire DICOM data and go through some DICOM to bits conversion process to make reconstructed images interoperable between different open source tools. But in case of Venus, we have the same user interface on both GE and Siemens, and using this interface, we define bits tags at the subject and session level, and after the acquisition, our data is directly exported in the bits format. The T1, MTR, and MTSET maps from vendor native acquisitions show a notable inter-vendor difference for the same participant, and these differences are not reflective of a true biological change in the myelin content. It's a systematic bias. On the other hand, when we use the unified vendor neutral sequence, we see a much better agreement between different vendors. Another common reproducibility problem that we face is caused by vendor system upgrades. Either planned or not, these upgrades happen at some point, and they may hamper the reliability of our longitudinal data collection for research purposes. Recently, our scanner went through a major system upgrade, and we repeated our experiment using the same participants, same scanner and coil, using the same protocol for both vendor native and vendor neutral acquisitions. I will show the results of T1 measurements in a quantitative system phantom, as we know it did not change before and after the upgrade. But after the upgrade, we observed a T1 underestimation between 0.2 to 0.5 seconds, corresponding to an 18.5% drift in our measurements. And this applied to both vendor native and vendor neutral workflows. But metadata showed a notable change for a specific parameter, and we were able to revert it to bring T1 values back to their original values. And I guess this highlights the importance of detailed reporting of hardware events during the acquisition. It should not be overlooked when designing open source acquisitions. But on the other hand, these results show that we need to standardize different aspects of our acquisitions, such as pre-scan calibration adjustments. So more work is underway to achieve upgrade immunity, yet open source acquisitions still provide some practical advantages against the system upgrades. For example, the way new upgrade introduced selection to export DICOM data, its enhanced or interoperability modes, and we didn't have them before. Both of these selections export images differently than the pre-app upgrade convention, so this requires us to update our data input and output management tools. Whereas vendor-neutral data export remained the same after the upgrade, as it took a community standard as a reference. So instead of being subjected to a choice made by scanner manufacturers, we stick with community standards and use the same scripts before and after an upgrade. When the user interface changes after an upgrade, our standard operating procedures change alongside with it. In cases, some options that were available may be removed. In other cases, new confusing selections may pop up. This requires additional efforts to ensure that we keep the acquisition as similar as possible to what it was. On the other hand, when we have a vendor-neutral user interface, we change it only when we need to. This way, improvements remain relevant to the needs of our research. Well, at this point, I hope that we have a better understanding of why open source MRI acquisitions matter for MRI measurements. So let's move from MRI to the scanners that are designed to actually measure things, PET scanners. So these scanners measure metabolic activity by detecting the gamma rays emitted from the body following the injection of radio tracers. And different radio tracers allow imaging of different metabolites, from cerebral glucose to beta amyloids. But of course, for accurate representation of metabolic activities, we need consistent acquisition and reconstruction methods. PET scans have a highly involved acquisition workflow. First, they need structural scans as external data, because PET images do not typically reveal structural details. In this study that includes 105 PET scans from 21 different centers, a variety of MRI scanners were involved, from 0.3 to 3 Tesla, and sometimes they didn't use an MRI. Duration of the PET scans are more operator and scanner dependent. For this study, it appears to be 90 minutes mostly, as you can tell by this color scale. But there are also different frame sequences to acquire for the data. Injected radio tracer dose may be different, and finally the reconstruction method can change from scanner to scanner. So as a result of this complexity, it can be difficult to infer whether an observed change is physiological or if it's driven by changes in data acquisition and or data processing. The open source landscape of PET is not as crowded as MRIs, but there is nicely documented reconstruction software on GitHub, which is named Agah, and it allows you to compare a wide range of reconstruction methods. Overall, PET has more variability involved in its workflow. DICOM support is not as good as it's in MRI, but hopefully we'll see more community tools developed to deal with these issues.
So I've been complaining about DICOMs, both for PET and MRI, but for EEG and MEG, there is not even a common data format. And on top of that, vendors rarely make their data specifications publicly available. So compared to MRI and PET, hardware is much less complicated, but it is not to say there are no differences between different acquisition methods. For example, MEG equipment implementation significantly differs between vendors. This example figure shows two MEG equipments. They have different sensor types with different spatial configurations. As a result, they pick up different features of magnetic fields and from different depths. So after recording MEG signals, researchers have to apply some proprietary signal space separation and noise suppression techniques to make the acquired data meaningful. For example, this Elekta Neuromag provides a method named MaxFilter, which is closed source. Fortunately, there has been some efforts on developing open versions of these proprietary tools. For example, MNE Python provides Maxwell filtering and signal space separation methods as open source, and they are all nicely documented. You can check their website. They also provide some example applications. In general, very little is known on how the variability of data acquisition parameters affect downstream comparability of results for EEG. There are initiatives such as OpenBCI, that stands for Open Brain Computer Interface, to provide open source EEG hardware designs. There is a bit extension for EEG to standardize acquired data along with the stimuli synchronized with task-specific timings, number of channels, electrodes, also supplementing information about the coordinate system. But to put these tools in better context, there is a big initiative called EEG Many Labs to understand replicability of EEG research. So you can follow them on Twitter to stay up to date about developments in this line of research. Finally, consistency in stimuli presentation is important for the reproducibility of the psychology experiments. You'd like to document the details of stimuli presentation, including your timing, intensity, duration, and all other relevant parameters to ensure transparency and reproducibility of your experiments. To make your life easier in doing so, you can use these open source tools. There is Psycopy in Python. It supports multiple modalities for experimental design and data collection. With recent additions, you can even run online experiments through a web browser, which is, I think, a really cool feature. There is then Pavlovia, a repository of shared experiments that are developed in Psycopy. Another tool that supports multiple modalities is Psych Toolbox if you prefer to use MATLAB. But if your research is based on event-related potentials, you can use the ERP core, which provides optimized paradigms, experiment control scripts, some example datasets, and data processing pipelines. Finally, there is ReproStim, a video capture and recording suite for neuroimaging and psychology experiments. It facilitates stimuli feature analysis and exact reproducibility of the experimental paradigms. So I hope you were able to find something to your taste in this presentation. If you could not, you can scan this delicious QR code to explore other components of the Oreo and I. And with that, thank you so much for your attention.